Good morning, my dear students. Welcome to the chemistry class. And today I will discuss the last group of your P block elements, that is the group 18 elements. They are also called zero group elements and they contain helium, neon, argon, krypton, xenon, radon. Okay. And they are also called noble gases or rare gases as their abundance is very low in the dry air or atmosphere, that is less than 1%. Next we will discuss the electronic configuration. Their outermost shells have the electronic configuration that will be NH2 NP6 except helium. Helium has 2 electrons and others also they are owing that octets, okay, or their octet is satisfied, okay. Now in case of helium that will be 1s2, in case of neon 1s2 2s2 2p6, that will be the electronic configuration. Argon it will be the 3 neon configuration, then 3s2 3p6, then krypton it will be 3d10 argon configuration 3d10 4s2 4p6, then xenon krypton 4d10 5s2 5p6, then radon xenon 4f14 5d10 6s2 6p6. These are the electronic configurations. Next we will discuss the occurrence. Except radon, all noble gases are present in earth atmosphere, okay. Argon is the most abundant noble gas, and in natural gas you will find 2 to 7% helium. And all of you know in sun atmosphere there is fusion reaction between hydrogen and they are forming helium gas, so 23% in sun atmosphere will be helium gas. Mineral like thorianite, pitchblende and monazite contains helium, okay. Certain spring waters also contains very small quantity, okay, of helium and argon, okay. And radon is not present in the atmosphere. Actually it is evolved by the disintegration of radioactive radium. When you are taking radium, okay, that will form radon as well as there will be formation of helium gas. Next we will go to the physical properties, okay. Physical properties. Here we are discussing according to your reduced syllabus. Physical properties. First we will discuss the monoatomic nature. All of you know that these gases, okay, they are highly unreactive, okay. Their octet and duplet is filled up, so definitely they will not combine with other atoms, okay, and they generally remains as monoatomic, okay. And these gases are colorless, odorless and exist in the monoatomic state. Monoatomic nature of noble gases has been confirmed by their CP/CV value ratio, okay. CP/CV value is close to 1.66. Next we will discuss the atomic radii. Now the noble gases have the maximum atomic radii in their respective periods. This is because atomic radii in case of noble gases are actually van der Waals radii, okay. So all of you know that van der Waals force, okay, here two atoms are coming very close and one electron is attracted by other nucleus and other nucleus is attracting this electron cloud of this atom, okay. Definitely practically there will be no overlap, okay, and you have to take the van der Waals radii by taking the half of the distance of the two nuclei. So definitely van der Waals radii, we know that it is greater than the covalent radii. So in other cases, in the other period elements, okay, we are considering the covalent radii, but here we are considering the van der Waals radii. That is why the radius is higher, okay, and maximum, and atomic radii will increase down the group as the number of cell increasing. When we are going down group, that means helium, neon, argon, krypton, xenon, radon, atomic radii will increase. Next we will discuss the ionization enthalpy. Now what is ionization enthalpy? The noble gases have high ionization enthalpies due to their highly stable electronic configuration, that is NH2 NP6, okay. Their octet is filled up, okay, so the ionization enthalpy is very high, okay, as they are highly stable. and whenever you are going down in a group, okay, definitely the size increases and the distance from the nucleus, okay, of the last electron increases, so their ionization enthalpy will decrease whenever you are going down the group, okay. That means from helium to neon, argon, krypton, xenon, radon in this way. Next we will discuss the electron affinity or electron gain enthalpy. Electron gain enthalpy. Okay. Now here already you know that their duplet and octet is filled up. Okay. In case of helium, it will satisfy the duplet. Other elements are satisfying that octet. That means they have the 8 electrons in their outermost shell. Thus, these elements have very little tendency to accept electrons. So these elements have large positive values of the electron gain enthalpy. Hope you can understand. Next, we will discuss the solubility in water. So you have to know that noble gases are slightly soluble in air or in water. Okay, the solubility generally increases with increase in the atomic number. Actually, what is happening here? This water molecule is polar and it will deform the electron cloud of these noble gases, and that is why there will be formation of dipole. Okay, and that noble gases will be soluble in water, and whenever you are going down, their size increases and their solubility also increases. Okay. Next, we will discuss the easy of liquefaction. So it is extremely difficult, okay, for noble gases to liquefy. It is due to the noble gases are held together only by weak van der Waals forces, and since these forces, okay, increases with increase in the atomic size, okay, so easy liquefaction increases from helium to radon. Okay, so when radon is easily liquefied compared to the helium, okay, and the helium will be the highest difficult to liquefy. Hope you can understand what I am telling. Next, we will discuss the compounds of noble gases. That means chemical properties. Compounds of noble gases. Okay. Now, xenon forms the higher number of compounds as compared to any other noble gases. It is because the low enthalpy of ionization, and xenon forms stable compounds, only the most electronegative elements like oxygen and like fluorine. So first we will discuss the xenon fluorides. Xenon fluorides. Okay, so xenon generally form 3 types of fluoride. One is HCF2, another is HCF4, another is HCF6. Okay, and these are prepared by the direct action of xenon with fluorine under suitable condition. Suppose when you are taking that xenon and fluorine in the ratio of 1:3, okay, that means fluorine gas you are taking excess, and here you have to use nickel tube, okay, and you have to use high temperature, okay, around 670 Kelvin and 1 bar pressure, okay, then it will combine and that will form HCF2. And if you want to prepare HCF4, then you have to take that xenon and fluorine in the ratio 1:5. Here also you have to use that nickel tube, to pass through this nickel tube, hot nickel tube, and temperature you have to apply here around 870 Kelvin, and here pressure required is higher compared to this one, around 7 bar, and here you will get HCF4. Okay. Next, to prepare HCF6, you have to increase the percentage of fluorine. Okay, so here xenon is reacting with fluorine in the ratio 1:20. Here also you have to take the higher temperature compared to this. Okay, now here as you are taking 1:20, so here around 580 Kelvin temperature is required, and pressure will be higher than around 60 bar. Okay, so here you are taking that nickel tube, and temperature is required around 570 Kelvin, and pressure is required around 60 bar, and then you will get HCF6. Okay, another preparation is there in your book, that is the another method, that you can take HCF4 and you can you can mix with O2F2, and around 140 Kelvin temperature you will get HCF6 and O2. Okay, so in this way also you can prepare xenon hexafluoride. Next we will discuss the xenon oxides. Actually in your syllabus now only structures are there. Xenon oxides, but you have to know the preparation also. Okay, xenon forms generally two types of oxides. One is XCO3 and another is XCO4. Okay, so one is tetroxide, another is trioxide, and this preparation method, okay, is generally done by hydrolysis of this HCF4 and HCF6. So you have to take HCF4 and you have to add water. So that means the hydrolysis of HCF4, that will give you xenon trioxide, and there will be formation of xenon, there will be formation of oxygen, and there will be also formation of hydrofluoric acid. Okay, now you have to balance this equation. Okay, so here you try to remember that here 6 and here 12, and that is why here 24 HF and chlorine also matched. Okay, next xenon. Okay, how much xenon is required will be found, that is 4Xc. So then it will be twice XCO3. Now you have to match the oxygen. Here 3 into 2 6, that means 3 into 2 6. Here 3O2. Okay, so in this way you can prepare xenon trioxide. Or simply another equation you can write, that HCF6 is reacting with water forming XCO3 plus HF. Okay, now you have to balance this equation. So here you have to put 3 and here you have to put 6. Now I think it is balanced. Okay, and xenon tetroxide is obtained by the action of anhydrous hydrogen sulfate, anhydrous sulfuric acid, okay, on barium pergenate. Okay, barium pergenate formula is Ba2, Ba2 XCF6, XCO6. This is barium pergenate. Okay, and here you have to add the sulfuric acid. From here you will get the xenon tetroxide, and you will get the barium sulfate, as well as you will get the water. Now you have to balance this equation. Okay, so here twice H2SO already written, so here you have to put 2, and here you have to put 2, Now I think it is balanced. Okay. Now xenon oxyfluorides. Xenon oxyfluorides. How to prepare xenon oxyfluorides? Fluorides of xenon, okay, that means oxyfluorides of xenon can be obtained, okay, by the partial hydrolysis of HCF4 and HCF6. Okay, suppose when you are taking HCF4 and you are giving water, definitely it will form xenon oxyfluoride, HCOF2 plus HF. Now here you see that fluorine is 2 here, so here you have to put 2. Hope you can understand what I am telling. And if you take xenon hexafluoride and here you are adding water, then it will produce HCOF4 plus HF. Okay. Now you have to balance this equation. So here already 4 taken, so here you have to put 2. Now I think it is balanced. Okay. So these are the xenon oxyfluorides. Okay. And HCO2F2 you can be prepared from HCF6 plus water. You will prepare HCO2F2 and there will be formation of HF. Now you have to balance. You have to balance this equation. Okay. So here you have to put twice H2 and if you put 4 HF, now I think fluorine is balanced, xenon is balanced, oxygen is also balanced. Okay. Next we will go for the structure. And last we will discuss the uses of these noble gases. Then your syllabus will be complete. So first we will discuss the structure of xenon difluoride, HCF2. HCF2 actually it is linear. Okay. Now if you look at the hybridization, it has sp3d hybridization. Okay. Shortcut method already I have discussed in class 11. That xenon means 8 electron is there, 2 fluorine is there, 2 divided by 2. So that means 10 by 2 means 5. So as 5 hybrid orbital is there, so it's definitely hybridization will be sp3d. And so it is linear. Here is the xenon. These are the equatorial positions are occupied by lone pair of electron, and these are the fluorines. So this is xenon difluoride. Okay. Next, xenon tetrafluoride, HCF4. HCF4 will be square planar. Here it has the hybridization, that will be the sp3d2. Here also you can calculate, that is 8 plus 4, that means 12 divided by 2, 6 hybrid orbitals. So definitely it will be sp3d2 and its structure will be like this. So this is the structure of xenon tetrafluoride. Next we will go for the xenon hexafluoride, HCF6. HCF6 actually it has the distorted octahedral structure. Distorted octahedral okay. Now the structure will be like this. And one lone pair is present. Okay, that is why it is not regular. Okay, because of repulsion of lone pair. And hybridization definitely it will be sp3 D3 hybridization. Okay, next we will go to the XCO3. Xenon trioxide. So its structure is trigonal pyramidal. Trigonal pyramidal. Structure will be like this. Okay, and hybridization will be sp3. Okay, oxygen we are not counting, that is 8/2 4 hybrid orbitals. So this is the structure of XCO3. Okay, next we will discuss the another oxide. Okay, that is the XCO4. XCO4 definitely here also it will be the tetrahedral. Okay, because here this lone position, okay, will be occupied by oxygen. Next in your syllabus there is xenon oxyfluoride, XCOF4. So structure of XCOF4 will be square pyramidal. So now here, this is the xenon, these are the fluorines, and here oxygen, and here one lone pair is present, and here 8 plus 4, that means 12, so this is sp3d2, sp3d2 hybridization. Okay, next I will discuss that XCOF2. Okay, so XCOF2, if you look at that 8 plus 2, that means 10 divided by 2, that means 5 hybrid orbital. So definitely it will be sp3d hybridization. So here it will be T-shaped. Okay. This is xenon, fluorine, oxygen. Okay, so it is T-shaped. Hope you can understand. So in this way you have to practice the structure, whatever in your syllabus it is there. Okay. Next, the last portion I will discuss about the use of noble gases. Helium is used as cooling, okay, medium in atomic reactors. Okay, oxygen and helium mixture is used to treat asthma disease. Helium 85% and hydrogen near about 15% mixture, okay, generally used for filling airships. Okay, and liquid helium is used for producing low temperature, okay, for research purpose, even magnetic resonance imaging, okay, that is MRI also it is used. Neon is used in the photography, okay, in fluorescent tubes along with other inert gases to get different lights. Okay, all of you know about neon lights. Okay, and it is generally used for the advertisement purpose also. And neon is used to stimulate the growth of the plants and formation of chlorophyll. And helium neon mixture is a bad conductor of electricity, and so it is used for protective devices for electrical appliances. Next we will go to the argon. Argon and mercury vapor is used in fluorescent tubes, and argon oxygen mixture is used for welding purpose. Argon nitrogen mixture generally we are using for the electric bulbs. Okay. Next we will go to the krypton. Krypton is used in radiological examination of respiratory organs. Krypton also used in electrical bulbs. Okay, as it is expensive, generally it is not used, but krypton when you are using in place of argon, it will be long lasting, that the bulb will be long lasting. Krypton is used in quick photography and safe landing of aeroplanes. Okay, and xenon is used as an anesthetics, and it is also used in quick photography. Okay, and next we'll discuss the radon. Radon is used in the ointments, okay, which is helps for treating in the cancer. So cancer, in cancer ointments, cancer disease ointments, okay, for curing cancer disease or different ointments, we are using this radon. And finally we will tell that this can be also used in locating the cracks, okay, in steel casting. Okay, so in this way we have completed the discussion of the P block. Hope you can understand. Okay, and if you have any question, okay, you can ask me in live classes. So today up to this, thank you.